So let's review what we just did in these examples. We defined the Lagrangian as the total kinetic energy of the system less the potential energy of the system. We defined the action as a functional of the path taken by the mass in the system. And then we use the Euler-Lagrange equation to find the true path, x of t, which minimizes the action. So now what we're going to do is take what we've learned so far and use it to generalize to a formulation which works for systems of many particles, many bodies, and also particles that are moving through multiple dimensions, not just one dimension. Imagine we have a particle in 2 dimensions. Its position is given by q1, q2, and therefore its velocity is given by q1 dot, q2 dot. And now let's add a second particle, and its position is q3, q4, and therefore its velocity is given by q3 dot, q4 dot. The important thing here is that we have 4 scalar positions and 4 scalar velocities. What I mean by a scalar position is in each pair of coordinates we have 2 scalar positions. The Lagrangian takes on the same definition in this more complicated example as the total kinetic energy of the system minus the total potential energy of the system. However, in this instance, the kinetic energy of the system is not just a function of one scalar velocity. It's a function of all 4 scalar velocities in the system: q1 dot, q2 dot, q3 dot, and q4 dot. Similarly, with the potential, we now have a function not only of one scalar position, but of 4 scalar positions. The action again is the integral of the Lagrangian over time between 2 discrete points in time. But now it's not just a functional of one position function, it's a functional of 4 position functions. And so now we have 4 different position functions, each of which, if we change it, it will change the action. So we have to find all 4 position functions which minimize this action. In order to do that, we have to apply the Euler-Lagrange equation 4 times, once for each position function. Therefore, we have, instead of a single differential equation, we have a system of differential equations, one for each position function. What if these 2 particles are in 3 dimensions? Well, it doesn't really change our approach. Now we have 6 scalar positions and 6 scalar velocities, but it's the same equations being used. The Lagrangian, again, it's the same thing, kinetic energy minus potential energy, except now the Lagrangian is a function of 6 scalar positions and 6 scalar velocities. The action is a functional of 6 different position functions. And we apply the Euler-Lagrange equation now 6 times. We have a system of 6 differential equations. So we use these Euler-Lagrange equations to solve for the scalar position functions, q1, q2, q3, and so on. For the sake of completeness, let's say we have a system where we have n scalar positions which define the system. Well, then we'll also have n scalar velocities. We'll have a Lagrangian which will be expressed as a function of n scalar positions and n scalar velocities. We'll have an action which will be a functional of n different position functions. And then we'll have n Euler-Lagrange equations. Now let's try to make this more complete by doing one more example. Now this final example is going to be a slightly more complicated example. We're going to have 2 particles and they're both going to be moving in 2 dimensions. So let's start here. Let's draw this out. So we have a 2-dimensional plane here, and we're going to have 2 particles. Now I'm going to call this particle A, and I'm going to call this one particle B. Now these particles are going to be connected by springs. The first spring is connected to the origin, and then the second spring connects both of them together. We'll give these springs spring constants Ka and Kb, and we're also going to give them natural lengths L1, or La, let's go with actually, and Lb. So we have particle A and particle B, and then we've got spring A and spring B. We're going to let the position of the particles be given by Q1, Q2, and Q3, Q4. So now we've set up this problem. Obviously we have gravity acting. So we have gravity, and we also have the springs acting. Okay then. Now, in order to solve this problem, it's just a two-step process. We have to build the Lagrangian, and then we have to enter the Lagrangian into the Euler-Lagrange equation. Now, the Lagrangian is going to be a function of Q1, Q1 dot, all the way up to Q4, Q4 dot. That's going to equal the kinetic energy minus the potential energy. Now, our kinetic energy. We have the kinetic energy in particle A, call that TA, and the kinetic energy in particle B, call that TB. Now, if we have a look at one of the particles, for instance, like A, let's say it's, call this part, this will be particle A. And let's say its velocity, it has some velocity. And we're going to let that be the scalar velocity. Then the kinetic energy is going to be 1/2 times the mass of particle A. So we obviously have different mass values for each of the particles. Well, it's not obvious, but we do. So we'll call that Ma, and the mass of particle B will be Mb, and multiplied by the velocity squared. But this velocity is comprised of the horizontal velocity, which is given by Q1 dot, and the vertical velocity, which is given by Q2 dot. And from Pythagoras' theorem, we know that V squared is just going to be Q1 dot squared plus Q2 dot squared. And so our expression for the kinetic energy of that particle A is going to be 1/2 Ma times Q1 dot squared plus Q2 dot squared. Okay, lovely. And then by similar logic and reasoning, we're going to have the kinetic energy of particle B is going to be 1/2 times the mass of particle B times Q3 dot squared plus Q4 dot squared. And so finally our total kinetic energy is going to be 1/2 Ma times Q1 dot squared plus Q2 dot squared plus 1/2 Mb Q3 dot squared plus Q4 dot squared. There we go. So now let's deal with the potential energy. So the potential energy, there's a few to consider here. First of all, we have the gravitational potential energy of particle A. We have the gravitational potential energy of particle B. We have the spring potential energy stored in spring A. And we have the spring potential energy stored in spring B. Now, the gravitational potential energies are pretty easy to figure out. the vertical positions of A and B are given by Q2 and Q4 respectively. So we can just say gravitational potential energy of A equals MA times G, gravitational constant, times Q2. Similarly, for the corresponding gravitational potential energy with particle B, it's going to be MB times G times Q4. Now the spring potential energies are a little trickier. So first of all, the spring potential energy stored in spring A. Let's try and zoom in on the situation here. So we have this spring, and it is going from 0, 0 to Q1, Q2, and it also has some sort of natural length. I'm calling that LA. Yeah. Okay then. Now, just like with any spring potential energy, it's going to be equal to 1/2 times the spring constant, Ka, times delta squared. And delta here is the amount that the spring has been extended or compressed. Again, the sign doesn't matter. Now, if we use some basic trigonometry, you can figure out that del is going to be the square root of Q1 squared plus Q2 squared minus LA. Reason for that is this entire length here we can calculate using Pythagoras' theorem. That's the square root of Q1 squared plus Q2 squared, and then we just subtract away LA. Okay then, and so now we have this equals 1/2 Ka times the square root of Q1 squared plus Q2 squared minus LA, and we're squaring the whole thing. There we have it. By basically the same logic, we can find the spring potential energy stored in spring B. It's a little trickier because we're not going from the origin. Instead, we have another pair of coordinates connected to Q3 and Q4, but it's the same process, and what we will arrive at is 1/2 times the spring constant B times the square root of Q3 minus Q1 squared plus Q4 minus Q2 squared, subtract away LB, the natural length, and then we square the whole thing. And so there's our expression. And then we add all of these expressions up to come up with the total potential energy. So there we have it. We have the expression for the kinetic energy there, the expression for the potential energy here, and then the Lagrangian is just going to be that full expression for the kinetic energy, so T function of Q1 dot all the way over to Q4 dot minus potential energy expression in terms of Q1 all the way to Q4. I'm not going to bother writing that whole thing out, but then once we have that expression for the Lagrangian, then we're just taking derivatives and entering it into the Euler-Lagrange equations. We're going to have 4 equations this time. That'll be our first one, but we're also going to have the Euler-Lagrange equation for Q2. And we're going to do this for Q3 and Q4 as well. problem is, what we have here is a very unruly expression for the Lagrangian. There's a lot of terms. If we were to take derivatives, we would have to use sequential chain rules a lot. It would take a lot of time to take those derivatives, and then eventually the differential equation which you'll be left with will be very complicated as well. So it's very difficult to do these analytically, if even possible at all. But what we can do is solve it numerically, using a programming language like Mathematica, for example. I'm going to demonstrate that now. So here we are in Mathematica, and so what we've got here, to start off with, I've defined the kinetic energy, the spring potential energy for each of the springs, gravitational potential energies, and then what we can do actually is, let's say the total potential energy equals V spring 1 plus V spring 2 plus Vg. Go with that. And then the Lagrangian is simply equal to the kinetic energy minus the total potential energy. Okay then. So then we have our Lagrangian here. Let's execute all of this. Right at the top. We've got our Lagrangian here. We created our differential equations. So these are the Euler-Lagrange equations. You can see the first one here is the partial derivative with respect to Q1 minus the full time derivative of the partial derivative with respect to Q1 dot, or dash here is what is used in Mathematica. And then we've iterated the same process for all four of our differential equations. And you can see the output here is those differential equations. You can see why it would have been quite bothersome to do this analytically, because they're quite complicated. Then in the next section, we set the parameters for each of those equations. So we basically just trivially set every single parameter just to 1, for example. And if you change those parameters, it will change the final dynamics. And then, so now we have our equations, our differential equations with the parameters set. And then here we use Mathematica's function for a numerical differential equation solver. So we plug in all four differential equations, and we also set in our initial conditions. So, you know, Q1 of 0 equals 1, Q2 of 0 equals 1, so on and so forth. And then we tell the programmer what which variables we're solving for here. And then it basically just solves it for us. So if we have a look at the output of this, it gives us what's called an interpolating function. So because it's done numerically, it hasn't found a smooth curve, it's just solved it for lots and lots of points in time, and that's why it's interpolating between those points. Then we just create our visualization here. So we have our solutions in the output here for the functions Q1, Q2, Q3, and Q4. And now we just animate those functions. So here you can see we've started off with these initial conditions, with the first mass here and the second one here. We've got our springs, which each have a spring constant just nominally set to 1. And then if we play this, let's have a look at how it acts. And what we observe is something which looks remarkably realistic. And this is what I find, I personally find this absolutely astonishing. Like, the fact that we have a single equation, the Euler-Lagrange equation, and just in combination with some knowledge about the energies in the system, we solve for this really incredibly complicated dynamical system. You can see how the springs are interacting and flicking around and whatnot. So there we have it. Those are the basics of Lagrangian mechanics. We went through how we define action, the fact that the true path which is taken in a mechanical system is the one which minimizes the action. and the fact that we have to apply the Euler-Lagrange equation to solve for the dynamics of the system. Essentially, all the problems boil down to is trying to define the Lagrangian and then just applying the Euler-Lagrange equation.